we have performed a welding process and obtained the joint. So before that, we have supplied the sufficient amount of weld metal into the welded section and obtain the welded joint. Now, after this, the solidification will happen. I am covering all the steps one by one. Initially, we prepared the joint and then transferred our weld metal into the welding zone. Now, we are letting our weld pool to solidify. After solidification, the bond will form, fusion will take place, and in the area near to the welded zone, some microstructural formation will take place. So microstructural formation is to determine or to understand the microstructure form. This formation is very important thing, and it will give you an idea about what will be the final microstructure when metal is solidified. And you know that the microstructure plays a very important role on the mechanical properties. In the welding process, the first thing is to obtain a defect-free joint, and the second thing is to obtain favorable microstructure. So favorable microstructure means the microstructure should have refined grain in the welded section so that it will result in the adequate strength and toughness. Now we will study how the solidification of weld metal takes place in welding. So where is the solidification taking place? The solidification is taking place in the fusion zone, which is a mixture of filler metal and the base metal that have completely melted. In the fusion section, your weld metal, which has been deposited from the melting of the electrode, it is getting solidified. And this solidification, how you can predict the behavior of the solidification? So scientists basically what they have done, they have predicted the behavior of solidification based upon this solidification phenomena happening in the casting process. The similarity of the solidification matches with the solidification of the welding process. If you remember how the solidification happens in the casting process, then you know that whenever you pour your molten metal into the cavity, the molten metal immediately starts to cool, and then it loses its energy to form the crystals. The crystals are small crystals, are made up of repetitive arrangement of atomic planes. The repeated joining of atoms in a predefined pattern results in the formation of crystals, and whenever these crystals joins together, more crystals join together at a particular site, it results to the formation of the grains, and whenever more grains are joined together, it will result in the formation of the microstructure. If you remember the solidification of metal, you might have seen that it is not happening quickly. On reaching the freezing point, the solidification does not start immediately. So what you have to do then, for initiation or the progression of the solidification, you require somewhat lowering of your temperature below the freezing point. That lowering of the temperature below the freezing is known as the undercooling, and this is the driving force behind the solidification phenomena, your solidification process. And as I have told you that when the weld metal cools down and during the solidification, these crystals are formed due to the nucleation. And if you remember from the metallurgy subject, then the nucleation is of two types. The first or the common type of nucleation is the homogeneous nucleation. For this homogeneous nucleation, you don't require any pre-existing sites. You don't require any particular defined particles to initiate the nucleation process. This is happening due to the lowering of the melt temperature below the freezing point, and for initiation of this particular homogeneous nucleation, you require a threshold size of the nucleant or the nuclei. So that particular size of the nuclei or the spherical nucleant is defined as the critical radius. Unless you achieve that critical radius, the nuclei which are forming in the melt or in the solidified material, they dissolve automatically. And if you achieve that critical radius, crystals will start to grow. Before that critical radius, these solid spheres or nuclei will simply remelt. And once you achieve that critical radii of the nucleants can be calculated with this particular correlation, which is R equals to gamma SL Tm over delta Hm into delta T, where gamma is the solid liquid interfacial energy, Tm is the melting point, delta Hm is the latent heat of melting, and delta T is the amount of liquid undercooling. This undercooling is cooling below the freezing point. So you know the undercooling, the melting point, the latent heat of melting, and if you know this interfacial energy, there are certain experiments by which you can calculate this interfacial energy, and based upon that you can predict the size of the critical size of the nucleants in the homogeneous nucleation. So once you achieve this critical radii during the solidification, your crystals will start to grow and they will start to join together and form a grain. So this is homogeneous nucleation. In majority of cases, this type of homogeneous nucleation is very less dominant in the solidification of casting, and rather another type of nucleation is in the dominating side, which is known as heterogeneous nucleation. In heterogeneous nucleation, the metallic grains are formed from the melt by the nucleation of solid particle or the crystals at the mold wall or any foreign particles. These are stable sites which have the lower energy and which also gives, you can say, the part to the conduction of the heat from that surface, and it results in the formation of nuclei of critical size. And sometimes to enhance this particular nucleation, you add oxides, you can add nitrites, sulfides, which will promote the heterogeneous nucleation. And once you achieve a homogeneous nucleation, your crystals or grain starts to grow. So that is called grain growth. These two mechanisms of nucleations happen during the solidification of the casting process, and similar type of nucleations are observed in the welding, in the solidification of the welded structure or the welded molten wood. After this, once the nucleation has occurred, the solidification proceed by the movement of solid liquid interface. If you can visualize that in the solidification section, solidification is starting from the mold surface. So some of the nucleants have resided or they have formed on the mold surface. In front of this solidified or the you can say the nucleation sites, there is a solid liquid interface which divides the solid part from the liquid part. Once the solidification proceeds, you can observe a movement or propagation of this solid liquid interface in the whole casting section. And during the solidification, whenever you are considering the pure metal, there will not be any solute. So there the undercooling is more dominant and it will promote the nucleation. However, in most of the cases, we are for engineering applications, we want to make a casting or the cast products out of alloy. During the solidification, the solutes are continuously rejected in the liquid in case of the alloy ahead of the interface. At one side, you have a solid surface. This is your solid interface. So this is your solid liquid interface, and here it is your liquid. So in that particular liquid column, the nucleation will cause the rejection of the solutes into the liquid, and this liquid ahead the interface, why it is rejecting the solute? Due to the decreased solubility in solute than the liquid. You know that particles are easily dissolved in the liquid phase rather than the solid phase. During the solidification, due to the solid solubility issues, they are getting rejected. And what is happening? At the same time, there is a heat ahead of the interface. So that heat is getting conducted from the solid liquid interface. From there, it moves to the solid portion and then it moves to the mold wall, out from the mold wall cavity. Due to that condition, the solid liquid interface becomes unstable. Earlier, the solid liquid interface was of plane shape, and due to the rejection of the solid and the movement of heat, this particular solid liquid interface becomes unstable and they form some dendritic like structure, means armed or branch like structure. That is called the dendritic microstructure. So initially a small arm grows out from the solid liquid interface into the liquid melt and it is getting solidified, and then after it sub branching will occur. So in the microstructure you might have seen dendrites. This is forming due to the rejection of the solid and the heat ahead of the solid liquid interface. This interface, which was of planar form, breaks down, becomes unstable and forms dendritic arms coming out from the solidified zone. Later on, as the growth of the crystal is occurring, it will result in the sub-branching of the dendrites. You will have the main dendrite coming out from the solidified zone and the sub-branching or tree-like structure from the main branch. And slow cooling makes the long dendrite, whereas the faster cooling results in shorter dendrites. With faster cooling, you don't allow the formation of these dendrites, and while in case of slow cooling, you are allowing the dendrites to grow. Multiple dendrites are growing into the solid liquid melt portion. When these dendrites are joined together, they form a grain of well-defined boundary. Within a grain, you can observe more dendrites that have joined together, and this will leads to the formation of a dendritic microstructure. Therefore, slow cooling leads to large grain structure, because there the crystal or grain growth will be more as compared to the small grains which have formed in the faster cooling. If you like the video, please subscribe to my channel, share it with your friends, and don't forget to hit the bell icon for the latest updates. Thanks for watching my videos.